Thank you for coming and joining me in my office in Stony Brook. This is work that I've been doing with Sultan Hamid and Lichuan Chi at, well, Lichuan was my graduate student. He got his PhD about 2 years ago and is now at the Skidaway Institute of Oceanography. And Sultan is at the same building I'm in, but he's an atmospheric scientist. And I've also had a lot of help from Charlie Flagg in the same building as me, who has been looking at the Gulf Stream for a very long time. This work has been funded by the NSF, and then the calculations were done on a cluster run by our Institute for Advanced Computational Sciences here at Stony Brook. Let's see if I can get this to work. There we go. So it's kind of the talk is in two parts. And the first one is going to focus on the interannual variability of the Florida current, with a focus on wintertime variability due to atmospheric forcing. And what we'll find is that there's variability associated with the Icelandic low at zero seasons lag, and the ASR is high at a 4-year lag. And then the second part is on Gulf Stream trends at Cape Hatteras and beyond. And the motivation there is that there's been a number of studies which suggest that the Gulf Stream is going to slow as the climate changes, and there have been also some studies which have suggested that it already has. And we're going to look at that, and we're going to find that, at least in our analysis, we find that the trends are relatively small. So these are both in two papers with the same crew here, and the first one, Sultan Hamid took the lead, and the second one, my former student Lichuan took the lead. And so the reason it's in two parts is because, well, Sultan would like me to talk about this, and we'd like to get some feedback on this aspect. And Lichuan is my former student, so I'm trying to boost his work, but hopefully there'll be enough time for both of them. And if not, I'll just focus on the first one. But so, you know, many of you are down in Miami, and so are familiar with the Florida current. Here's just a picture, the classic picture of sea surface temperature, showing this warm streak of water going past Florida and out into the Gulf Stream. And the Florida current is this chunk here. And then in particular, the strength of the Florida current has been monitored across the Straits of Florida since the early 80s. And the Florida current has an important in a number of aspects. It's sort of the first major western boundary current that people really looked at in any detail, or at least the Gulf Stream is, and the Florida current is the headwaters of the Gulf Stream. But it also plays an important role in at least basin-wide climate, if not global climate, because it's an important gateway for the Atlantic meridional overturning circulation. And is in fact monitored as part of the RAPID project to quantify the strength of the Atlantic meridional overturning circulation. A big chunk of it goes through the Florida Straits. So the mean transport of the Florida current is about 32 surdrips, and it's observed both by a cable going across from Florida to the Bahamas, and then many calibration cruises that get the two-dimensional structure of the thing from LADP and SADPs. As I mentioned, it's been monitored by a cable stretching between Florida and the Bahamas. This is a retired telecommunications cable, and you can determine the strength of the current by monitoring the voltage across the current. This is simply because the ocean is a conducting fluid, and it's flowing through a magnetic field, and Maxwell's equation says that will give you a potential drop, and you can basically you do a bunch of calibration cruises to figure out what the proportionality between the voltage and the transport is, and then you can monitor the transport with a temporal resolution it's very difficult to achieve any other way. And of course, AOML maintains the Western Boundary Time Series project, and they make available this transport estimate. This is actually a figure from one of Dennis Volkov's recent papers that shows the cable data in black, and then other ways of trying to estimate the transport, both with an eye of what to do if the cable breaks, and also to try and fill some of these gaps that occur in the record due to instrument losses or various things. So we're going to talk about Florida current. Sorry? No. Okay. We're going to talk about Florida current variability, and I mean, you can see this thing wiggles back and forth really rapidly, and it has variability on a wide range of scales, and in fact, most of the variability is at annual and sub-annual time scale, something like 80% of it. But there is some remaining variability of the other 20%. And it's been attributed to a number of different processes, one of which is the upstream of the Florida current, there's the loop current, which sheds eddies irregularly, and that will reduce the transport. And this happens on sort of a 12 to 13 month time period, but it's not particularly regular. Other people have shown that eddies propagating in from the east will affect the transport, but there's been a lot of interest in a long time trying to assign the role of atmospheric forcing to the fluctuations of the western boundary current. And part of this is simply because, the classic theories of ocean circulation say that the western boundary current should be proportional to the wind forcing over the basin. And so if you change the wind forcing, you ought to change the transport. And then the question is, can that be quantified, and how much, and can it be made quantified in a way that's predictable? And so we're going to focus on atmospheric forcing. The sort of go-to way of sort of representing the state of atmospheric forcing over the Atlantic is the North Atlantic oscillation, NAO, which is it's a fluctuation in the strength of the Icelandic low, which is sitting up here by Iceland, and the Azores high. And the modern way of quantifying the state of the NAO is to form an EOF of sea level pressure, and this is the loading pattern shown for the winter time using Harrell's PC-based index. And you can see that it's associated with an increase in pressure in the Icelandic low and a decrease in pressure in the Azores high, or vice versa, because it's an EOF, so it's sign invariant. And high values of the NAO correspond to high Azores high and low Icelandic low. And so, and then this is the sort of the wind stress. The vectors are wind stress, and the contours are wind stress curl associated with a 1 standard deviation fluctuation of the NAO in winter. And so you can see it affects the wind stress curl, and then we think through Schroeder theory, this should affect ocean circulation. And so people have tried to look at fluctuations in the Florida current and relate them to changes in the NAO, and with varying success. Barringer and Larson showed that there was a time period where there was correlations with the NAO for annual variations. And more recently, D'Annunzio showed that the NAO was correlated with wind stress curl to the east of the Florida Straits, not directly with NAO, but just the wind stress curl out here. But there was only a 67% confidence on that. But the suggestion is that because if you change the wind stress curl to the east, you can stimulate baroclinic Rossby waves, which will propagate westward and impact the Florida current with some delay. And a typical way of generating those is to cause a fluctuation in the NAO, and that causes a change in the wind stress curl, and a baroclinic Rossby wave is created. However, more recently, Chris Minden has shown that the correlations with the NAO do not persist outside of this original interval, and so they're intermittently correlated, and there's these transient things that happen to them. And so we thought we would take another look at large-scale atmospheric forcing, but instead of thinking about it just in terms of the NAO, we're going to think about it in terms of the component pressure centers of the NAO, which go back to, I believe it was Rossby that named the original, Carl Gustav Rossby, called them centers of action. And they're basically semi-permanent highs and lows. Here's the Icelandic low, here's the Azores high. And they have their own, they don't just sit and fluctuate in strength, they also move around. They change latitude and longitude. And the NAO is a 1D representation of all of those possible configurations of these two pressure centers. Sultan, my collaborator on this, constructed indices which represent the latitude, strength, and longitude of the centers of action. And basically, for the Icelandic low, we have this sort of blue box, and we take the mean pressure below a certain threshold as the strength, and then the latitude and longitude are the pressure-weighted center of mass. And then the same thing with the Azores high, just with a high pressure instead of a low pressure. And this figure here shows in contours, it's the mean sea level pressure in wintertime. And then the little blue dots are each one is the position of the Icelandic low at a different winter, a different year, and the same thing with the Azores high. And then these are the fluctuations in pressure of each one of them. And so the idea here is that these 6 individual indices can represent atmospheric states that are not captured by the NAO. And obviously, there's going to be some redundancy, so we always have to keep that in mind when we're interpreting these. Since I showed you this sort of pattern associated with the NAO, the wind stress and wind stress curl pattern associated with the NAO, I ought to show you the same thing for the different indices of the Icelandic low along the top and the Azores high along the bottom. And then we have latitude, longitude, and pressure going from the left side of the screen to the right. And you notice that especially for the pressure indices, there's a lot of similarity with the NAO. The pressure index for the Icelandic low is sign flipped with respect to the NAO because the NAO is a difference, or approximately a difference. But the pressure indices look a lot like the NAO, with the exception that the Icelandic low pattern is more concentrated in the north than the NAO. And the longitude indices also look fairly like the NAO, but they have stronger wind stress curl in the south, just a little bit. And then the zero wind stress curl lines are slightly different, which is important. And then the ones that stand out as being very distinct are the longitude responses. So it's the things migrate back and forth. It changes the wind stress over the ocean and the wind stress curl, and the pattern of changes that it produces is very different from the pattern produced by changes in the NAO. So what we're going to do is we're going to look at the Florida current transport, and we're going to use the cable data as our input data, and we're going to deal with the gaps by filling the monthly transport with altimetry. When we can get it. Dennis Volkov worked out a proxy, an altimetric proxy for the Florida current transport. And then before 1993, when we don't have altimetry, we fill it using linear interpolation. And then we focus on the winter time. And this is a strong influence of my collaborator, Sultan Hamid, because winds are much stronger and variable in the winter. And so it's natural to segregate everything by season. And then additionally, we focused on the wintertime variability of the Florida current transport. And there are, and so that's what I'm going to talk about today. There are other significant correlations with the centers of action in other seasons, but this is the one that we've looked at in detail so far. And so what is shown up here is the winter Florida current transport values going from 1984 to 2017. And I mean, the peak-to-peak variation is a little bit less than 10 SIRDRIPs, which is decent compared to the mean. And then these are the correlations between the NAO and then the various centers of action indices and the Florida current transport at various lags. And the bold ones are the ones that are significant at the 95 99% confidence threshold. In fact, this one and this one are significant at 0.02, p less than 0.02. And so what we find is that there is a significant correlation at 0 lag with the longitude index, and then at 4 years lag with the both the latitude and the latitude indices of the Icelandic low and the Azores high. But the Azores high is the one that stands out, and the Icelandic low one is the correlation is smaller and the significance is smaller. And it turns out that these two latitude indices are highly correlated. So this is probably just a carry on. The Icelandic low latitude one is a carry on from the fact that there's a correlation with the Azores high latitude. Usefully or significantly, there are no correlations with the NAO at any lag. And the best significance you can get is p equal 0.26, which is not particularly significant. So what we're going to do is we're going to look at the mechanisms behind these two, the correlation at 0 lag and the correlation at 4 years lag. And we're going to focus on the things that are distinctly different between the Icelandic low this is the longitude index. Sorry, this says latitude. It should be longitude, and the NAO. And so if we compare the two, the major differences are, well, one, the direction of the wind stress at high latitude is different. There's southeasterly rather than northeasterly subpolar winds, and then there's this extra thing of negative wind stress curl off of Africa. But it turns out that what's happening out here doesn't really matter that much. It's all just the stuff that is happening close to the coast. And basically the positive wind stress curl here is stronger. It projects slightly further north, and then it's difficult to see here, but the arrows are a little bit more along shore down here, and then the cross shore arrows up at high latitudes are a lot weaker, and we'll see how that becomes important. The way we diagnose this is, stepping back a little bit, we said, okay, we have these correlations, and we have all these indices, and so, okay, a correlation just says that they're related or they covary, and it doesn't tell you necessarily that there's any kind of causation. And so to get to assess that, whether there could be any correlation, at least for the 0 lag, so that's lag within 1 season, we put these wind stress curl patterns, or just the wind stress patterns and the curl follows, into a numerical model as an anomaly. The thing was running with its regular climatology, and we put in these anomalies and checked to see how the Florida current transport evolved. And the model that we chose was the ECHO V4 1 degree ocean state estimate. The reason we chose that was because we thought that the background state mattered a lot. And ECHO V4 has a good background state. It's a highly constrained ocean state estimate. As it turns out, the background, at least for the 0 lag correlation, it doesn't matter that much because the responses are essentially linear and they're fast. And so we tried several different years, thinking that maybe the background state evolving would change, and it doesn't matter. It's all the same. And so we're just showing the results from one particular winter. And the way that we did is we put in the anomaly, ramp it up linearly over 1 day, and just hold it constant for the season as just sort of a big hammer to hit the ocean with, and applied at the beginning of December 1. So our winter here is DJF, the sort of the atmospheric winter, December, January, February. And these are the anomalies of Florida current transport following the application of the perturbations. And the thick orange one is the Icelandic low longitude one, the one that we find has the large correlation. And we see that in this model, it also has the largest response. The transport goes down rather abruptly, sort of recovers a little bit, and then wanders off and keeps getting the anomaly keeps getting stronger. Now, in reality, none of these anomalous conditions would persist, probably not even for the whole winter, but definitely not longer than the winter. And so, you know, if we were making a more realistic perturbation, we'd have it tail off at the end of winter and it would recover, but we just cut it off here. And then we put in all the other ones just to see what they would do, and they actually kind of sort themselves in the way that you would expect, in the sense that the Icelandic low longitude one has the larger response of all of them. And then the interesting thing is that we put in the NAO as well, and it actually has about the weakest response of any of them, which was initially kind of surprising. So how does this evolution happen? Why do we have this rapid adjustment and then a fall off and then this gradual strengthening? So we're gonna look at that in a little more detail. First, I'm gonna show you an animation of the sea surface height anomaly associated with this perturbation. So we put the perturbation on at day 0, and then the sea surface height evolves, and it's going to go by too fast, so we're going to look at it in greater detail in the next couple of slides. So I'll just start it. Oops, no, actually I didn't even start it. There we go. So you can see something happens real fast. The sea level at the coast goes up rapidly. There's this high that forms out in the middle of the ocean, and then there's a low that forms at high latitude, another low that forms at low latitude. But as I said, it goes by fast enough that you can't really tell what's going on. But pointedly, at the end of 30 days, which is out here, if you look at the Florida Strait, there's this high at the coast and then a low offshore, and so that by geostrophic balance, that would reduce the transport through the Florida Straits, because in the resting state, sea level is low at the coast and high offshore, and so this is counteracting that. So we're going to sort of go by day, not every single day, but day by day, and I've changed the orientation of the plot somewhat so that it all fits nicely, but you have to kind of tilt your head if you want to look at it like it's on a globe. So Florida's here, and this is Newfoundland and Nova Scotia. So here's the east coast of the United States, and the gray blobs are just the model topography, because I didn't want to put on a fancy looking coastline because it ended up covering some of the actual data. And then here's the little section that we're using to measure the Florida Straits transport, the Florida current transport. And then this contour we're going to come back to. It's not really a contour, it's black line. This follows an F over H contour starting at the deepest part of the Florida Strait, and then it goes up. And so we'll just look at the initial evolution. I'm gonna let this flicker a few times, but you can see that the coastal sea level builds up real fast, and then there's this sort of larger scale high that's further out away from the ocean, or away from the coast, and what is causing this sea level high is simply just the coastal winds. It's a direct response to the coastal wind anomalies. So here's a little here's the alongshore and cross shore winds, and the way that they're plotted is I'm following, this is basically it follows the 200-meter isobath, this contour, except I've simplified it by going across, say, the St. Lawrence Channel and stuff, so it doesn't just zoom in there. But basically, it follows pretty close to the 200-meter isobath, which is kind of the shelf break, or the edge of the shelf on the East Coast, and then the tip of Florida is at 0. And then way up here at 6,000 kilometers is Labrador, and these things tick off 1,000 kilometers for each one along the path. And so this is the longshore wind with downwelling being over here, and this is the winds associated with the Icelandic low longitude. And this is the cross-shore wind with onshore winds being the blue and offshore winds being the red. And so what we can see is that sort of for the whole eastern seaboard, south of the Grand Banks, there's downwelling favorable winds, and that would tend to push water onshore which would raise the sea level at the coast. And in addition, there are onshore winds. So on short time scales, before a couple of inertial periods kick in, the onshore winds also push water to shore. And then where there's a lot of friction, you can't get quite the exact, if there's friction against the bottom, you get a little bit of downwind drift too, and so the onshore flow matters. And then if we go further up the coast, we see that there's now upwelling favorable winds sort of off of Labrador and Newfoundland, which will tend to depress the sea level. And then there's offshore winds further north off Labrador, which again will depress the sea level. And so basically what happens is you get this setup of sea level along the coast south of Newfoundland, and then that propagates southward as coastal trapped waves of various flavors, and that accumulates the response. And then this low will propagate around and cut off the response after about 5 days, which is what we see here. And so if we go back to here, you can see the coastal setup here all along up to Nova Scotia and Newfoundland, and then the set down up on Labrador. And then by the time we get to day 5, this setup has gotten even stronger and is, started moving its way around Florida. You can see that there. And then the low associated with this offshore wind and upwelling on Labrador has started creeping around Labrador. And from day 5 to 15, it starts propagating down and around and makes this sort of trough in the sea level high. And we can kind of see how that evolves. And as that's happening, so actually this is from day 1 to day 5, sorry, I got a little bit ahead of myself. So the sea level is building up because there's this kind of sort of highish sea level off here has propagated towards the coast and been replaced by a low, which is driven by wind stress curl in the open ocean. And then there's a high up here, which is driven by the opposite sign, wind stress curl in the open ocean. And so this is where the peak occurs at 5 days, where all this stuff is squished up against the coast. This is the peak suppression. And then as we go further in time, now we see that the wind stress curl is, or not the wind stress curl, the response decreases from day 5 to about day 15. And this corresponds with the arrival of this upwelling signal coming around or low coastal sea level signal coming around Labrador and down the coast. And it's kind of difficult to track with your eye, and especially it's actually more prevalent in bottom pressure than it is in sea level. And so to quantify this better, this is a Hogg-Muller plot of the bottom pressure divided by rho times g, so it's equivalent height, equivalent centimeters, along this F over H contour. And so you can see that when you're down here around Florida, the bottom pressure also picks up to day 5, and then you get this signal propagating down the coast of a reduction in bottom pressure, and it propagates down the coast at about 6.5 centimeters per second, which is kind of in the right ballpark for a continental shelf wave. And when this arrives, it reduces the Florida current response, and it also makes it more baroclinic. Before this, the response was mostly barotropic, just driven by sea level changes. And then once this wave arrives, this bottom trapped wave arrives, the response shoals and it becomes more baroclinic. And this response to shelf waves has been seen by other people. Beal in 2008 found evidence of shelf wave impacts on Florida current transport. And actually, we'll talk a little bit, I'll mention it briefly later, but an adjoint sensitivity study by Seychelles et al. Also found that coastal trap waves of various flavors influence the Florida current transport on short time scales. So once we get to 15 days, so we'll just watch the evolution of things as we move towards 15 days. And you can see that there's a little bit of an impact on sea level, but it doesn't show up quite as dramatically because it's mostly in bottom pressure, as I showed on the previous slide. But the main thing that is also happening from 5 to 15 days is that this high is growing in strength and sort of moving in towards the coast, and some of the high sea level is making an impact on the coastal sea level. And then this low is also sort of, well, it's intermittently propagating, and we'll find that as time goes on, this low becomes even lower. And in fact, that's what we're going to get to right now. So once we get past day 15, we start this sort of long asymptotic, or long 90 days increase in the response. And that's mainly due to this buildup of both this this high up north, which is affecting coastal sea level, which then propagates down, and then this low. Both of these are driven by wind stress curl, but this low depresses the sea level offshore, and so you've got the sea level going up onshore and down offshore, which is increasing the response. It's increasingly tending to reduce the Florida current transport. And if we look at just a Hogg-Muller diagram of the evolution of sea surface height across the Florida Straits, starting from the beginning of the perturbation all the way to 90 days, you can see what I just said. Basically, initially you get this rapid setup of sea level right at the coast, and then that slowly sort of builds and then saturates. And then the thing that keeps the response going is this buildup of low sea level offshore. And so you're relaxing the sea surface height gradient across the straits. So that's the lag 0. So that's 1 season lag. And that it makes sense also that this should be a wintertime thing, because the very strong changes in wind occur in wintertime. And so this response can happen almost synchronously from a seasonal time scale. If we look more at the 4-year lag response, this is going to be more of a plausibility argument rather than a detailed dynamical, well, a detailed model experiment, essentially. So if we look at, if we regress the Florida current transport anomaly on the wind and the wind stress curl with a 4-year lag, this is the wind stress and wind stress curl response, or not response, forcing or field that was present 4 years prior to the anomalous Florida current transport. And we can compare that to the thing that has the high correlation, the Azores High Latitude Index, and perhaps not surprisingly, because there's a correlation, the patterns look pretty similar. It's more of a sanity check than anything. But the long time lag, the 4-year time lag, suggests baroclinic planetary waves, because they're about the only thing that takes that long to do anything. And sort of following in D'Annunzio and many others, in fact, we suspect that the changes in the wind stress curl at low latitude, so east of the Florida Straits, are driving or exciting baroclinic Rossby waves, which can then propagate eastward and affect the Florida current transport. And so for that to work, the Azores High Latitude Index has to explain a lot of the variation in the wind stress curl at those latitudes, and in fact it does. So this is the colors are just the same thing as here. It's just the wind stress curl regressed on the Azores High Latitude Index. But the contours, the black contours, are the fraction of the variance of the wind stress curl that is attributable to the Azores High variation itself. And so we're getting 30%, 40%. So it has a big impact on the wind stress curl in winter. And so then we ask, well, how long would it take a wave to get from sort of this, sort of the open ocean to the Florida Straits. And so we need some estimates of baroclinic wave propagation times, and we have some from Kilworth and Osinchny. And the crossing times, if we were to launch a wave from the Mid-Atlantic Ridge, and I'll tell you in a second why we think it's the Mid-Atlantic Ridge, it would take about, on average 2 years to get to the Florida Straits, which is shorter than the timescale that we see. But the second mode would take about 4 years, and so there's at least it's at least not physically implausible. And some extra plausibility comes from this adjoint sensitivity study by Seychelles et al., who also looked at the effect of coastal trap waves on Florida current transport on shorter time scales, but the relevant fact here is the longer time scales. And so what is being shown here is the adjoint sensitivity to the wind at various lead times. And so you can see this of adjoint sensitivity to the Florida current transport to the zonal wind stress, leading by 2 years and leading by 3 years. And you can see that there's this sort of wave packet looking thing that is propagating backwards in time. So if you were running this forward, it would be coming in this way. And they diagnose this as being due to wind-driven changes to currents flowing over the Mid-Atlantic Ridge, which then generates a baroclinic Rossby wave off the bottom, and this one, or off the ridge itself. And this one turns out, in fact, to actually be a mode 2 wave. So this is a Hobb-Muller diagram of these sensitivities. And they do get a sensitivity to something that moves at a mode 1 speed, but it has a rather fast propagation time, and the sensitivities are not that large, and it kind of dies out right about here, which is where the Mid-Atlantic Ridge is. Whereas the mode 2, well, it also comes from the Mid-Atlantic Ridge down here, but it has a much larger response and propagates basically in roughly the right time scale to the Florida Straits. And as I said, we're not the first people to implicate baroclinic Rossby waves as modulators of the Florida current, and a number of people are listed here. The most recent, this Kostov, is again a adjoint sensitivity study, but it extends out. It's actually looking at the AMOC instead of Florida current transport, but because the Florida current transport contributes so much to AMOC, the results are essentially consistent with what we find. So the conclusion to the sort of the part 1 bit is on the interannual variability of Florida current, is that the interannual variability of the Florida current is associated with changes in the Icelandic low longitude at 0 lag and the Azores high latitude at 4-year lag. And the Icelandic low longitude shifts are associated with coastal winds which set up the sea level south of Newfoundland and sit down north of it, and this happens very quickly. And then on longer time scales, sort of on a month time scale, negative and positive wind stress curl anomalies offshore create sea level highs and lows that then affect the Florida current through geostrophy. And then the longer lag response is likely due to second mode baroclinic Rossby waves that are excited by the changes in the wind stress due to the changes in the latitude of the Azores high. And for more details, I encourage you to check out this paper. The next part is relatively brief, so that's good because I have relatively little amount of time. But again, we're back at Florida, or we're back at the Gulf Stream, but now we're going to look at what's happening past Cape Hatteras. And the reason for this is that a number of studies have suggested, well, and this is IPC AR5, which just shows the response of the Atlantic meridional overturning circulation to various climate forcings. And they have different ideas about what the actual transport is, but they all agree that the AMOC should slow down as we increase the buoyancy at high latitudes. And since the Gulf Stream carries the return flow of the AMOC, the Gulf Stream should slow down too if this happens. And there's been studies which have examined this directly, like for instance this paper by Chen et al, where this is the historical CMIC-5 Gulf Stream, and then this is the response, the RPC 4.5 minus the historical, and you can see that the Gulf Stream itself has slowed down over this whole range, and in this case it's slowed down by about 14% by the end of the century. And then there's other mechanisms by which the Gulf Stream can slow shift or shift northward that have to do with changes to the northern recirculation gyre, which I won't go into the details of, but there's a literature starting with Zheng and Vallis 2007 that covers this. Now the question so I think most people would agree that the AMOC is probably going to slow down. This is probably going to affect the Gulf Stream, and the question is, has it already? And a number of studies have used indirect or indirect to more direct ways to infer the strength of the Gulf Stream and suggested that it has been slowing. So there's been a couple of studies that infer based on coastal sea level that the Gulf Stream has been weakening since 2004. Various studies based on gridded altimetry or hydrography or sea surface temperature have suggested that the Gulf Stream has shifted northward and broadened. Other people have suggested it's shifted southward, so there's not total agreement in the literature. There's a recent paper by Dong et al. Also found a southward shift in the Gulf Stream and a weakening, although interestingly, this is from gridded altimetry, and then a few in situ observations were analyzed in the same study, and no significant trends were found at those points, which agrees with studies by Rossby and Sanchez-Franks et al. That in situ observations haven't shown that there are any significant trends in Gulf Stream properties. So, where do we come in? Well, what we did is we wanted to get good coverage, so the whole Gulf Stream, but we wanted to get as close to the actual data as we could for data that had good coverage in time and space. And so we used a long track altimetry at these tracks. And the reason we picked these tracks is that they cross the Gulf Stream at close to 90 degrees, not quite, but the other set of tracks is much more oblique. And what this figure shows is the mean path of the Gulf Stream, the tracks, and then the blue is the sea level across the Gulf Stream, and then the orange is the velocity, the cross-track velocity. And we use long track altimetry at the native time resolution. We don't do any smoothing or low pass filtering or anything, except we use seasonal averages. And you can use monthly means, it doesn't make any difference. Annual means just gives you larger confidence intervals. And the things that we derive from the long track altimetry are the maximum geostrophic velocity downstream, the latitude of the maximum velocity, surface layer transport, which is the geostrophic velocity integrated between the 0 points, and then the E folding width of the Gulf Stream. And then we do this at all tracks except for 152, because 152 gets too close to Cape Hatteras and we can't calculate the transport of the width, so you'll see a gap in the next couple of figures. And the way we just calculate the trend using ordinary least squares, but we try to be very careful about confidence intervals. And the way that we figure them out is once we've fit this trend, we have a residual, and we fit that residual to an ARP process, an autoregressive process using maximum likelihood. And then we figure out the order using the Bayesian information criteria, and we go up to p greater than less than 13 just for computational. This is also, well, this is a very long time. Going to larger ones doesn't make much difference. This is what we used it. And then the way that we calculate the confidence intervals is we have this t statistic, which is slightly different from your standard t statistic because it's got this decorrelation time in it, which is defined like this, where this is the the autocorrelation function determined from this AR process fit, and then this weight, which you can just calculate if you just do the maximum likelihood estimation for ordinary least squares with an AR process. You just get this weight out, and this was done by Lee and Lund, and so you can check that out. And then this is the residual variance here, which is just the regular variance, except that you use the effective degrees of freedom rather than the actual degrees of freedom. And so then we just use the t-distribution to find the confidence intervals. So the first thing we do is we find the decorrelation time, and this is the decorrelation time at the various tracks for latitude, speed, transport, and width in season. And what we find is that the decorrelation time for most places is actually a season, so it's just one, in which case all the formulas just reduce to standard confidence intervals for standard ordinary least squares, and so we can use that to check against just standard statistical packages, and we get the same answer. Except there's a few places where the decorrelation time is rather long, sort of just downstream of Cape Hatteras. The Gulf Stream is very sticky there. If we use, instead of seasonal data, if we use monthly data, we get the same result, except some of these come in at slightly less than 3 months. So the whole thing is internally consistent. So what do we find? What are the trends? So this is using data from 2000 or from 1993 to 2018, which was all the altimetric data we could get when we did this. What is shown here are trends in per decade trends in latitude, speed, transport, and width, with red being positive, and then latitude is in kilometers per decade, blue being negative, and then the error bars are the 95% confidence intervals. And what we find is that there are only 4 trends which are statistically significantly different from 0. There are 2 in latitude, very close to Cape Hatteras, 1 in speed, sort of further downstream, and then 1 in width, even further downstream. And so, okay, 4, great. However, we are doing 42 statistical tests. So at the 5% confidence level, you expect 1 in 20 of those to have to pass just by chance. So we expect to get 2 to 3 significant trends, even if there were none, and we got 4. So maybe 1 or 2 of them are real, but we don't really know which one. If we look at speed and we say, okay, well, not everyone. Some people say that the Gulf Stream is slowing down, but we find that the only significant trend for speed is positive. And we'll say, well, maybe it's really getting broader. But the only significant trend we find for width is getting narrower. So it's not. Basically, the point is we don't find evidence that the Gulf Stream is getting slower or broader. And you could say, oh, well, maybe you're being too conservative with your confidence intervals. What if you went to the 90% or something like that? These bars give you the confidence threshold at which these things would become significant. And so the 95 is this dashed line. So you can see the ones that pass the 95% confidence interval. If we cranked it down to 90%, we would expect 4 to 5 to be significant by chance, and we would get 6. So we're still back to about 2 to 3 significant trends. At 80% confidence, we'd expect 8 to 9, and we get 10. So again, no matter what you do, you only get 1 to 2 more significant trends than you would expect based on random chance. Now, so again, the upshot of that is we don't see any evidence that the Gulf Stream is slowing or broadening. Now you could say, well, maybe there are really trends, but the record is just too short. And the record, I mean, essentially that's what I am saying, is that the record is too short to find trends because there's so much variability on top of it. So we can ask, well, how long would the record need to be if we assume that the trends that we have are the correct trends, and that the noise is stationary? How long would it take for the trend to become significant? and we can ask this question. And this is each bar gives the number of years it would take total for the trend at that track to be significant. And this little dashed line is the length of the data set that we have here. And then, obviously you can pick one or two and say, it's going to be at this time, it's going to be at this time. But we thought we're looking for why, if the whole Gulf Stream is changing, we should have widespread changes, right? So we picked our threshold to say at what point could we detect significant changes at least half the tracks. And so that's what these year things are: 48, 70, 41, 49 years are here. So what we would find is that we would have to wait at least another 15 years to see widespread trends in latitude. We'd have to nearly double the record to see widespread changes in width or transport, or latitude or transport, sorry. Width is the 15 years. And then to see significant changes in speed, we have to nearly triple the altimetric record, which is just a long way of saying that we'd have to wait a long time. Now, while we were putting this out, working on this Dong et al. Study came out, which does something very similar to what we do. They calculate the width, speed, the position, sort of in stream-centered coordinates, but they use gridded altimetry instead of along track altimetry. And then they also low pass filter instead of seasonally average. And then they also have a slightly different time period that is considered. And they find that actually there are some significant trends, especially out to the east, especially in position and speed. And then this is proportional to transport. But they note that these trends are extremely sensitive to the time interval in which you use. And so we said, well, what if we use the same time interval as Dong et al.? Well, so if we recalculate it using the same time interval, we get this picture here, which is a lot closer to what they see, and is similar, but significantly different, significantly in the non-statistical sense, from what we get from just changing the amount by 2 years, the amount of data by 2 years. And so in a certain sense, we agree with Dong et al. In that the magnitude of the trends is extremely sensitive to the amount of data you actually use, which suggests that even the formal confidence intervals we're using here might be too misleadingly narrow, because you say, okay, well, this trend is significant here, but if we had 2 more years of data, it suddenly becomes insignificant. And so was this really significant in the first place? A mystery that has plagued us that we can't resolve yet, and I would love to have some commentary on it, is why our confidence intervals remain smaller than the ones shown in Dong et al. Or our confidence intervals are larger. So we find very few statistically significant trends, whereas they find many more. And that's mainly because of the difference in the width of the confidence intervals, not the difference in the size of the trends. But that is currently an unknown mystery. And so the summary for the second part is that we find that the trends in the Gulf Stream properties at Cape Hatteras are small compared to the variability. And most trends are much smaller than their confidence intervals. And we'd have to wait a long time to detect the trends if they are as big as we've calculated them to be. And since we don't, since our confidence intervals are so broad, we don't have a lot of confidence in the trends themselves either. And this paper was published in GRL recently, so I encourage you to take a look at that too. And with that, I'm done.